Hello, in this video I will be solving a problem on projectile motion, and it's taken from the 1986 edition of Bostock and Chandler's book called Further Mechanics and Probability. It is exercise 5a, problem 6. Let me read the problem aloud. A particle is projected with an initial velocity vector 50i plus 30j plus 50k from the point with position vector 5i minus 3k, where I and k are horizontal and j is vertically upwards. Find vector expressions for the velocity and position of the particle at any time t. If the xz plane is ground level, find the time of flight of the particle. Find also the vector equation of the plane that contains the path of the particle. Here, the lowercase letters I, j and k are orthogonal unit vectors in the x, y and z axes respectively. I will also write down the vector equation of the plane in the standard and Cartesian vector forms and include an animation of the trajectory of the particle. Assumptions. There is no air resistance. There is no spin. During its flight, the particle experiences vertical acceleration only, which is directed downwards. There are no other external forces, such as wind force, acting on the particle during its flight. Here, the acceleration due to gravity is denoted by the lowercase letter g and is taken as 10 meters per second squared. Acceleration vector. The acceleration vector a is equal to 0i minus gj plus 0k. Velocity vector. The velocity vector v is equal to the integral of the acceleration vector with respect to time. Therefore, v is equal to c1i plus open bracket c2 minus g times t close bracket j plus c3k, where c1, c2 and c3 are the integration constants. The initial conditions. At time t equals 0, the initial velocity of the particle is given as u equals 50i plus 30j plus 50k. Therefore, at t equals 0 seconds, v is equal to c1i plus c2j plus c3k. To find the integration constants c1, c2 and c3, we equate the initial velocity vector to the velocity vector at t equals 0, which gives c1 equals 50, c2 equals 30 and c3 equals 50. Therefore, we can write the velocity vector as v of t equals 50i plus open bracket 30 minus 10 times t close bracket j plus 50k. Position vector. The position vector r is equal to the integral of the velocity vector v with respect to time. Therefore, the position vector r is equal to open bracket c4 plus 50 times t close bracket I plus open bracket c5 plus 30 times t minus 5 times t squared close bracket j plus open bracket c6 plus 50 times t close bracket k, where c4, c5 and c6 are the integration constants. The initial conditions. At t equals 0 seconds, the initial position vector r0 is equal to 5i plus 0j minus 3k. And the position vector r at t equals 0 is equal to c4i plus c5j plus c6k. To find the integration constants c4, c5 and c6, we equate the initial position vector to the position vector at t equals 0, which then gives c4 equals 5, c5 equals 0 and c6 equals negative 3. Therefore, the position vector r of t is equal to open bracket 5 plus 50 times t close bracket I plus open bracket 30 times t minus 5 times t squared close bracket j plus open bracket 50 times t minus 3 close bracket k. Time of flight. The flight of the particle starts at the ground level, the xz plane, and ends when the particle returns back to the ground. Therefore, the position vectors y component will be equal to 0 both at the start and at the end of the particle's flight. Therefore, referring back to the position vector derived above, we can write y is equal to 30 times t minus 5 times t squared. Now, substituting 0 for y gives the second order polynomial equation 30 times t minus 5 times t squared equals 0, which has the two roots, t equals 0 and t equals 6. T equals 0 seconds corresponds to the instant when the particle is launched, and t equals 6 seconds corresponds to the instant when the particle returns back to the ground. Therefore, the time of flight is 6 seconds. The vector equation of the plane. To obtain the vector equation of a plane, we choose 2 points that lie on the plane. If we now call one of these 2 points A and the other one R, then the vector AR equals the vector OR minus the vector OA, where O represents the origin. Now, if we take a normal vector at A, then the angle between the vector AR that lies on the plane pi and the normal vector n is equal to 90 degrees. Therefore, by taking the scalar product of the vectors AR and n, we get open bracket r minus a close bracket dot n equals 0. Therefore, the scalar product of the vectors r and n is equal to the scalar product of the vectors a and n. If we now let a dot n equals the uppercase D, then the vector equation of the plane can be written as r dot n equals uppercase D. This can be written in the standard vector form by dividing both sides of the vector equation of the plane pi by the absolute value of the normal vector n. Therefore, the scalar product of the vector r and the normal vector n divided by its own absolute value is equal to the uppercase D divided by the absolute value of the normal vector, where the unit vector n hat is equal to the normal vector divided by its own absolute value, and the lowercase d is equal to the uppercase D divided by the absolute value of the normal vector. The lowercase d gives the perpendicular distance from the plane pi to the origin. The equation of the plane in the Cartesian form. The vector r is equal to xi plus yj plus zk for any point on the plane pi, and the vector n is equal to n1i plus n2j plus n3k. Therefore, the scalar product of the vectors r and n is equal to n1x plus n2y plus n3z. Therefore, we can write n1x plus n2y plus n3z equals uppercase D, which is the Cartesian form of the equation of the plane. Finding the vector equation of the plane containing the path of the particle. The vector equation of a plane is r dot n equals uppercase D. To obtain the normal vector n, we can select 3 points that lie on the plane pi1. Then, using these 3 points, we can obtain 2 vectors that lie on the plane pi1. Once we obtain these 2 vectors, we can then take their vector product to find the normal vector n. From the above sketch, we see that 3 points A, B and C are chosen. And using these 3 points, the following 2 vectors that lie on the plane are formed. The vector AB equals the vector OB minus the vector OA, and the vector AC equals the vector OC minus the vector OA. Using the initial launch position information, we see that the point A has the x, y, and z coordinates 5, 0, and -3 respectively. Therefore, we can set the vector OA equals 5i plus 0j minus 3k. Now, taking the point B as the point when the particle returns to the ground at the end of its flight at t equals 6 seconds, and taking the point C as the point when the particle reaches its mid-flight at t equals 3 seconds, we can obtain the vectors OB and OC as follows. At t equals 3 seconds, the vector r is equal to open bracket 5 plus 50 times 3 close bracket I plus open bracket 30 times 3 minus 5 times 3 squared close bracket j plus open bracket 50 times 3 minus 3 close bracket k. Therefore, the vector OC is equal to 155i plus 45j plus 147k. And at t equals 6 seconds, the vector r is equal to open bracket 5 plus 50 times 6 close bracket I plus open bracket 30 times 6 minus 5 times 6 squared close bracket j plus open bracket 50 times 6 minus 3 close bracket k. Therefore, the vector OB is equal to 305i plus 0j plus 297k. Therefore, the vector AB is equal to the vector OB minus the vector OA, which is equal to 305i plus 0j plus 297k minus, in brackets, 5i plus 0j minus 3k. Therefore, the vector AB is equal to 300i plus 0j plus 300k. And the vector AC is equal to the vector OC minus the vector OA, which is equal to 155i plus 45j plus 147k minus, in brackets, 5i plus 0j minus 3k. Therefore, the vector AC is equal to 150i plus 45j plus 150k. Now, the cross product of the vectors AB and AC is a vector perpendicular to the plane pi1 and directed upwards as shown in the above sketch. Therefore, we can set the vector AB cross the vector AC is equal to the normal vector n. Therefore, expressing the vector product of the vectors AB and AC as a determinant, we get the vector AB cross the vector AC equals minus 13,500i minus 0j plus 13,500k after expanding the determinant, which can be written as AB cross AC equals minus 13,500 times, in brackets, I plus 0j minus k. Therefore, the normal vector n can be written as n equals I minus k. If the vector A is equal to 5i minus 3k, then we can take the scalar product of the vectors A and n to obtain the value of the uppercase D. Therefore, A dot n equals open bracket 5i minus 3k close bracket dot open bracket I minus k close bracket. Therefore, A dot n equals 8, which means the value of the uppercase D is 8. Therefore, the vector equation of the plane pi1 that contains the path of the particle can be written as r dot open bracket I minus k close bracket equals 8 in the vector form. In the standard vector form, the scalar product of the vectors r and n hat equals the lowercase d. We have the absolute value of the vector n equals the square root of 1 squared plus negative 1 squared. Therefore, the absolute value of the vector n is equal to square root of 2. The vector n hat is equal to square root of 2 over 2i minus square root of 2 over 2k. The lowercase d is equal to 8 over square root of 2. Therefore, the lowercase d is equal to 4 times square root of 2. Therefore, we can write r dot open bracket square root of 2 over 2 I minus square root of 2 over 2 k close bracket equals 4 times square root of 2. This is the vector equation of the plane pi1 containing the trajectory of the particle written in the standard form. From this, we can see that the plane pi1 is perpendicular to a vector having direction ratios 1, 0, -1, and the distance between this plane and the origin is 4 times square root of 2 units. The Cartesian form. The Cartesian form of the vector equation of the plane pi1 can be obtained by taking the dot product of the position vector r and the normal vector n. Therefore, r dot n equals uppercase D, where the vector r is equal to xi plus yj plus zk, the vector n is equal to I minus k, and the uppercase D equals 8. Therefore, the Cartesian equation of the plane pi1 is x minus z equals 8. The following animation shows the trajectory of the particle in the plane that it lies on. This brings me to the end of this video. Thank you for watching.